We will now turn to the examples in Lesson 61. Example 1. The position of an object moving in a straight line is given by this formula, S of t, where time is greater than or equal to 0. And t is the time in seconds, and S of t is the position of the object relative to some origin in meters. We will answer the following question. A. Find the velocity and acceleration of the object at time equals to 2. B. When is the object at rest? C. In what direction is the object moving when t is equal to 3? And D. Find the average velocity of the object between 0 and 3 seconds. On your IB exam, you will be given reading time before you actually start writing your solutions or answering questions. It's very important that when you read your exam or read the question, you start formulating ideas as you read them. So when I, like number 1, or part A here, when I see velocity acceleration at a certain time, well, I cannot find the exact instantaneous velocity and acceleration unless I have the actual function. So I know that first I will need to figure out my equation. I don't know why I'm putting primes here, but S prime and S double prime, right? When I see buzzwords like when the object is at rest, I know that we're talking about 0 velocity, 0 speed. From your investigation, we learned that the direction of an object is based on the signs of your velocity function. Seems pretty important here, right? We're talking about velocity in parts A, B, and C. In part D, however, since we're looking for the average velocity of an object, well, what does average mean? You add everything up, all the velocity up, and divide it by the total time. But does it really make sense? It doesn't, right? So in another way, we can think of, well, on average, we have traveled a total distance over 3 seconds. Wouldn't that be the average velocity? Well, strictly speaking, is not really distance here because velocity is vector. So let me fix this. I should be saying displacement instead. Over total time. Now we make the physics teacher happy. Okay? All right. Let's begin with part A. In order to find the velocity function, v of t, we are going to take the derivative of s of t. This will give us, 5.4 plus 6.4 t minus 3 times 1.2, 3.6 t squared. We can continue to find a of t because this is simply v prime of t. So first term 0, 6.4 is next minus 7.2 t. With these functions, we can now calculate v of 2, 5.4 plus 6.4 times 2 minus 3.6 times 2 squared. What does that give me? I believe it gives me 3.8. You can check that on your calculator. And when I substitute 2 into the acceleration function, 6.4 minus 7.2 times 2, you can use a calculator for this. You can get negative 8.0 meters per second squared. B, when is the object at rest? This time we're going to set v of t equals 0. v of t is a quadratic, so 5.4 plus 6.4 t minus 3.6 t squared equals to 0. As too complicated to, factor decimals, let's take out the quadratic formula. 6.4 is negative b plus or minus b squared minus 4 A, which is negative 3.6, C, 5.4. Let's square root this whole thing over 2 times negative 3.6, okay? You very carefully punch in these numbers onto your calculator. You will either get 0.62 negative or t equals 2.4 seconds. We know that since t is greater than or equal to 0, this is an inadmissible root. Inadmissible. There we go. As a result, the only possible answer is 2.4 seconds. Number 3, or part C, in what direction is the object moving when t is equal to 3? That's good because this gives us a specific time that we're looking for, and all we care about is the positive or negative sign at 3 seconds. Okay. Let's plug this in. We have 5.4 plus 6.4 times 3 minus 3.6 times 3 squared. It works out negative 7.8 meters per second. We can write down, therefore, the object is moving in the negative direction. Do I have room? No. That's it. Last but not least, we're going to look at question D. We're going to find the average velocity, which requires us to find the displacement over total time. Displacement is the direct linkage. So, for example, if point A is here, point B is here. One person move along the path, that's how they get from point A to point B. Another person decided to take a direct path. Another person went around before they reach point B. All 3 people have different distances, but the same displacement, because their change in position remains the same. They got from A to B. And when we talk about displacement, we are really talking about the blue one here. Okay, this is the total displacement. As a result, I don't really care how they got there. Okay, I just know that they were in position as of 3 at 3 seconds, and at position as of 0 at time 0. Sorry about that. And then times 3 minus 0. Okay. If I work this out, S of 3 gives me 12.6. S of 0 gives me 0 over 3 here. It works out the average velocity of this journey is 4.2 meters per second. If you would like to take a look at the graphs of question 1, that's what they relate. That's how they relate to each other. Okay. Try to identify how the zeros, for example, how the 0 match up with the max here. Do you see any meaning for the zeros in position versus velocity? Maybe there's a relation, maybe there's none. What about the maximum that we see at VT? How does that relate to A of t, and so on and so forth. Next, we will look at example 2. Example 2 says, a ball is thrown vertically upward from the ground and its height in meters after t seconds is given by s of t equals to 20t minus 5t squared. Let's label this graph. This is time. This is time in seconds. And this is s of t in meters. We're going to find the velocity at t seconds. Find velocity at 1.5 seconds. When is velocity 0? Greatest height. And the velocity when the ball hits the ground. So it's before it comes to a stop. If you would like to pause the video first and come back to see the solution, feel free to do that. It's actually recommended. Okay, I hope you have had a chance to try the questions, or at least come up with a strategy of how you're going to approach each part in this question. A, v of t in general is s prime of t. So we have 20 minus 10t. Did you get that? With a general v of t function, now we can find v at 1.5 seconds. This is 20 minus 10 times 1.5, that's 15. So this is 20 minus 15, 5 meters per second. Part C. When is the velocity 0? v of t equals 0. 20 minus 10t is equal to 0. T must be 2 seconds. Easy so far, right? D, we're asking for the greatest height reached by the ball. Greatest height. You have a diagram, so you can maybe get some hint from it. It's a parabola. You can read off the graph that, okay, it's going to reach the greatest height at 2 seconds. And it looks like the greatest height is 20 meters. Let's try to confirm that. One characteristic about this is called free falling object. Okay, when we toss the ball up and then gravity is just going to bring it down to the ground, is that when the ball reaches the maximum height, it actually reaches 0 velocity. Some of you may not notice that. Okay, it momentarily stops and it changes direction. Does that sound familiar? So now for part D then, at maximum height, v of t is equal to 0, and we already know that it was 2 seconds, right? We found that in part C. As a result, we can plug in s of 2 into the position function 20 times 2 minus 5 times 2 squared. This is 40 minus 5 times 4, which is 20 meters, which matches with the graph that we have. When is the ball's velocity, what is the ball's velocity when it hits the ground in part E? We know that because it is starting from the same height as where it's going to land, which is on the ground, by symmetry, we know that it's going to hit the ground at 4 seconds. Okay, let me write this down. Then we can sub in v of 4 into the equation of v of t. So 20 minus 10 times 4. 20 minus 40, negative 20. Are you scared to see that negative sign? You shouldn't be, because it's exactly what we are looking for. When the ball is coming down, is coming down in a negative direction, so the velocity must be negative.